Hello, friends. Welcome to the Georgia Tech AI podcast. My guest today is Sean Wilson, the branch chief of collaborative autonomy at the Georgia Tech Research Institute. Sean's work focuses on bridging the gap between theoretical robotics and real world implementation. With a background in physics and math, his interest in the collective intelligence of desert ants led him into swarm intelligence. As a postdoc at Georgia Tech, he helped turn the Robotarium from a tabletop idea into a globally accessible platform. If Sean has one core belief, it is this: robotics research should work in the real world. And now, dear friends, please welcome Sean Wilson. So, what is it about collective behavior in nature that still fascinates you on a personal level?
Yeah, so whenever you see any swarm roboticists or anyone who studies swarms, when they look or give a talk, um, you never see a collective of people. They might show, like the classic Tokyo crossing or something like that. Um, but what's really interesting about swarms is that humans are really bad at them. And I find that fascinating, right? There's not a lot of good intuition that I can bring to this problem. So I really enjoy the cross-disciplinary nature of this problem set and requiring to look elsewhere and understand things that are not intuitive to me, but I can still kind of bring some intuition to and solve the problem with.
Can you give me examples of swarm like behavior? I know that a large part of your PhD was dedicated towards studying desert ants. Could you paint me a picture of what you were trying to replicate there?
Yeah, so when I started my PhD, my advisor showed me a video of ants collectively transporting something. So these were, back then, they were Aphenogaster cockerelli. They've since been renamed to Novomester cockerelli. But the idea was basically they took a fig out into the desert, they dropped it in the desert, and these ants magically show up. They automatically form their teams. They bring it back. There's no pheromone trails, which is something people usually think, oh, they're just smelling their way back, but they're not. And so they magically form this team. It's a stable team. They do stable transport. They're avoiding grass and gravel and rocks and things. And it's a miraculous picture. And the reason they do it is that the is very food scarce environment. And so what they need to do is get it back as soon as they can to the ant colony. If they don't, something else will come take it. So they don't have time to chop it up and bring it back. That motivating picture is really what spurred my PhD. Is that I do not think at that time, and even now, it's still hard. You could get, if I were to drop something and say robots go get it, and you had 100 robots, I don't think 10 of them would magically figure out how to get there. Would magically pick it up, without talking, without having some centralized controller. It's a miraculously cool thing that they do, and they don't have any real we don't have good ways of replicating it, right? We don't really understand fully how it's done, and we don't really understand fully how to replicate it.
Wow. So, what do we understand currently about collective behavior, and what's still left for us to have this be replicated on real robots?
Yeah, so biology is hard. I also do not claim to be a biologist. I had great collaborators at ASU. Orle Buffin and then Stephen Pratt and Ted Pavlik were my bridges to entomology. And for my limited understanding is that it's really hard to prove anything. Similar with humans, right? If you bring them into a lab and put on a lab coat, right? It's really hard to say anything concrete, right? Because there's diversity, there's lots of hidden variables. You can't really isolate and test like you can in robots. Really what we wind up doing, the reason that this bridge between robotics and entomology works so well is that you can go in nature, you can understand the limitations of the individual things that you're studying, right? The ants, the bees, the termites, the whatever. So then you have a sensor capability, you have actuation capability, and then you have a hypothesis on what they might be doing. And you can test it in nature, but only a few times really. But with a robot, right, you can throw that algorithm on and run it a million times. The robots will do the same thing every time. And so you can prove things in that way. You can say the robotic experiment with some standard deviation looks like it did it. And you can say this is a possibility on what they are doing. But you really can't say this is definitely what they are doing. That's a much harder claim to make. And I leave that over towards the biologist colleagues.
So, it seems like we still haven't reached the kind of collective magic that happens in nature. What is the difference between multiple robots, the multi robot systems as we have it today in warehouses, agriculture, and the swarms that we see in nature?
Yeah, so there's two differences. One is goals, right? Nature's goal is, people always say it optimizes, right? It's survival. At the end of the day, right? It's survival is the thing that they are optimizing, and what we are trying to do with warehousing and things like that is really optimize throughput of the factory, optimize some sort of factor. And in nature, these are truly independent entities, and they have we can have an argument about this, but they have much higher levels of autonomy than any of our robots do currently, right? If you had the autonomy level of a bird or even an ant, right, that can perceive and move around and make decisions, that's a really, really hard thing that we do not have yet. So all that to say, the second difference besides just the goals is the way that we implement these things. It is really hard to robustify robotics. I think if you talk to any roboticist, right, getting it out into the real world is hard because it needs to work all the time and generalize. And we don't have that yet. So the way that we kind of circumnavigate that in warehouses is we usually have these things centralized. So there's one server or a few big servers that are commanding everything, keeping track of everything, which doesn't scale really well. And they're well instrumented, right? You have tracking systems, you have maybe markers on the floor. The famous is the KUKA robots. My favorite example, right? Is navigation is really hard if you have your eyes closed. And so the way that they solve that is they put stickers every 2 feet, so you know exactly where you are. And that's a brilliant solution, but it doesn't generalize out to the real world well.
Right. You said autonomy. And at least what I'm thinking is the whole tension between centralization and decentralization. So you mentioned that in warehouses, you have a centralized controller and it doesn't scale well. It's not even robust. If I take the central piece out, the whole system crashes. But with ants, if I take one ant out of the collective transport example, the thing still moves. There'll be more ants joining in. What are you trying to do in terms of ensuring that collaborative autonomy is something that we can achieve?
Yeah, so I think it's hard, and I don't think there is a solution. The classic phrase I use when I teach or anything is a pick your poison, right? There's a spectrum of solutions. When you get towards the ants, it's completely decentralized, it's completely robust, right? Each individual is making their own decisions, reacting to the environment and others, and this makes it scalable and robust to failure and all of those good things. But what's really hard about those kind of systems is you can't really guarantee a lot because each individual agent is making their own decisions. You can usually make kind of, if you model the entire system as a group, you can kind of guarantee what they will do or bound it, but you can't really say very hard guarantees what they're going to do. Versus if you go towards a centralized system, I have this centralized controller. I know exactly what it's going to tell everyone. I know exactly how it's going to measure everyone, and so you can make much harder guarantees. So when we talk at least collaborative autonomy, so the branch that I run at Georgia Tech Research Institute, we're really trying to find the right spot in that spectrum based on the problem set that we are trying to solve, right? Because currently, in my opinion, again, have arguments. I think robots are currently idiot savants. They are really, really good at specific tasks. They don't generalize well.
What is the North Star vision for you in terms of ensuring that collaborative autonomy is something that permeates our daily life? What kind of a future do you imagine?
Yeah, so I would love to have multiple robots doing so the classic. I heard this from DJ Kumar. I don't know if he's the originator of it, but the dull, dirty, and dangerous, right? You want robots that are doing dull tasks, so stocking shelves and things like that. Dirty tasks, cleaning out sewers, going through septic tanks, things like that, and dangerous, right? Out in minefields, Fukushima nuclear reactor meltdowns, right? You don't want to send people into those kind of environments. Where I see collaborative autonomy and multi-agent robotics going through is they're robust individual failures. You send a really expensive Boston Dynamic Atlas, right, and it's doing backflips and doing amazing things through the factory floor. But if its leg snaps, it's over, right? But if I sent maybe 100 less expensive ones and 10 of their legs snap, we're still good. So the North Star vision is being able to send robots into these extremely dangerous, hazardous environments and be able to solve the tasks in a way individuals cannot. Additionally, the North Star vision currently is just to get them out there. It is really hard, right? You don't see a lot of multi-robot systems outside of, you can kind of massage and say Waymo cars or Tesla autopilots, right? They're kind of there, and you can say that the warehouse robots are collectives, but you don't really see a lot of truly collective robots, and there's a lot of fundamental challenges out there. One of my favorite is that I'm not at all involved in is how do you control them? Like a single human getting hundreds of robots information how do you digest that? How do people digest it? People are working on it, but it's a fundamental challenge to show how young this idea is.
It's so practical though. I know you mentioned that your key research focus is taking the theory, the algorithms, and putting it to real robots, seeing it actually work in a robust manner. But you didn't start off like that. You were a physics and math undergrad, and then you moved into robotics at ASU. Can you point that exact moment where you said, "Okay, I've had enough of deriving proofs all the time," and move to real robotics?
Yeah. So I'm a very practical minded person. Well, in the beginning, I said, you know, if I like swarms because I can't really intuitively understand it. In physics, I got it started getting towards quantum and Einstein notation for EM, and my brain just started breaking a little bit. Right, I couldn't intuitively understand these things, and I could do the math, but I didn't like that my brain couldn't intuitively picture stuff. Math was the same deal, right? I've always viewed math as a tool. I'm good enough at it, but when I'm doing theorem proofs and you know I'm trying to map it to analogous things in reality, that's where my brain was like, this is not for me, right? I don't have the passion here. And I always loved computer science, but when I was in undergrad, my father said something along the lines of like, computer science is going to be outsourced, right? It's not a good thing to go for. So, you know, do a more fundamental, you know, something that you enjoy but is more human oriented. And so I didn't do it. But so at that point, right, I'm at the end of undergrad. I've done physics, I've done math. You know, I have this strong foundation, and I like computer science. I said, what's the intersection of these things? It's robotics, right? So I started sending out applications to do robotics. And when I started, because I had such a theoretical background, I was really doing theory, right? I was doing dots on screens. I was doing some simulations, and again, it didn't feel right to me because I felt like I was making things up. And if I didn't see it in a physical thing moving, then I didn't really believe in what I was actually making. And so that's like the bridge that brought me to, all right, I want to implement things. I started becoming a middleman once I built all these robots to theoreticians that would put things on my robots. And you know, that's when the spark ignited, and I was like, you know, there's a need for this middleman. That can translate the theory into the practical hardware and at least validate, right? Get an idea that it can work. It might not be robust, but it can work and maybe just needs a little massaging.
Absolutely. What led you to Georgia Tech? Because I know that you started off as a postdoc and worked at the Robotarium, but I would love to see that journey when you entered probably 8 years, 9 years back.
I met Magnus Egerstedt at a conference in Japan, and we sort of were talking about this idea of having real robots needing to put things in real robots. And he had told me about this Robotarium idea he had. And so he showed me this little tabletop and he said, the vision is to let anyone in the world submit things and let them run. And so I said, that's an amazing idea, right? I'd love to be a part of it. You know, that's a great idea. So a little while later, got recruited to Georgia Tech as a postdoc. In about 6 months, had to take that tabletop and put it into a full room, let people have access to it, all that good stuff. And then it was mildly successful. So we were running, you know, 10, 20 experiments a month, right? Nothing to scoff at. We were still doing something no one's ever done. And then take it like 6 months later, we really didn't do ad campaigns or anything, but we started going up to like 500. I remember the first month we hit 500. I was basically in there with some of the other grad students running things simultaneously all the time, right? We're just running it. And what was really hard was because it wasn't our experiment, we didn't know if the experiment was bad, right? Their code was bad, or if our robots were breaking, or if the tracking system wasn't going right, or if the Wi-Fi wasn't, communications weren't correct. And so it was really hard to diagnose. And so I started this real push of we need to automate this whole thing, right? We need to have really robust robots. So I designed the GritSpot X, which is now the G-Ternal, and you know, put a lot of work into automating this thing. So now the Robotarium is at a state where you can submit something, no one's in the room, it will wake up, it'll run the experiment, it'll go back. Things still break now and then, right? But that's the journey that brought me into Georgia Tech, and I've never left, right? Still keep doing collaborative autonomy, but that was my initial step.
Right. I mean, it's incredible because if anyone thinks about Georgia Tech robotics, one of the first things that they see on campus is the Robotarium. It's had a profound effect on the student community and outside as well. I think it's definitely higher than this, but last I read it was 15,000 experiments in every continent except Antarctica. That's actually really impressive.
Yeah. It's now I think 16,500, something like that. Every continent except for Antarctica. I need to reach out to that research station and just be like, send here's an example script, send it, right? Yeah, that would be great. And then it is a visual showpiece. And that was Magnus Egerstedt's idea, which now I've come to appreciate more, which is it needs to be visually appealing, right? It needs to be inspiring. It needs to be something where, right, we bring K through 12 students through, and it really, I always say that I think that robotics can be a gateway drug to math and science, right? I will learn trig all day long if I'm navigating a robot, right? But if you're just drawing triangles, sine of 30 does not matter to me at all.
Well, that's also something you do in your own class. I know I speak to a lot of grad students, and they tell me that CS 7785, Introduction to Robotics Research, is their favorite because whatever you teach in class, they apply in the lab, it's like in a day or two. So, what do you feel are key components of a successful robotics education that leaves that impact, that leaves them to pursue the important research questions?
Yeah, so I think what's most important, or at least the motivating factor. So this was a course 9 years ago. Whenever I joined Georgia Tech, I helped co-develop with Sonia Shinova. So I don't want to take full credit for any of this. Um, but the main idea was we wanted to have a class that was broad, right? We didn't dive deep into anything, but gave a full spectrum uh, shot of a robotics system, right? So you saw the impact of controls, hitting perception, hitting planning, hitting machine learning, right? Just being able to see everything. And then most importantly of all of that, understanding why you were taking other classes, right? A lot of robotics curriculum can get really heavy into math, can get really heavy into computer science. And it's easy for students to lose the why I am doing this, right? Why am I doing nonlinear Lyapunov stability proofs, right? And so by giving open-ended questions in these labs. So rather than saying use an RRT to do a path planner, it is here's a bunch of waypoints. I'm going to throw stuff in front of your robot. The only goal, hit the waypoints, don't bump into stuff, right? And that kind of open, we still teach in class. If you don't know anything, give you a method to solve it. But that open ended, you make mistakes, figure out just how to get it done, right? And then when you're done with it, we can have a talk about optimization, right? What is the best way to do it? And then we'll come back to my mantra of pick your poison, because there is no optimal, right? It's with respect to a cost function. And for some students, I've also go up and say, hey, your cost function is getting an A in this class, right? Minimal effort, maximal grade. That is totally fine. But if you were doing, putting more into it, maybe here's a better way to solve it. So towards a robotics curriculum, right? What's important? I think implementation is extremely important, right? Putting stuff onto a robot, you have to do it at least once. And then giving students the opportunity to see the full spectrum, right? They're going to have a big contribution to a very small chunk of it, but understanding all of those components interacting, I think, is extremely important and needs to be pushed in early on.
Well, it's also on a personal note, just seeing the robot act autonomously and behave like an intelligent entity, it's incredibly gratifying. It makes you fall in love with the subject and want to learn more. Do you still have those moments of bewilderment where you're just, oh wow, I love this field? Do those moments happen every now and then?
Yeah. Yes, they still do, and it's probably from a similar thing. I just have, that happens when I implement things on bigger robots now. But I think where I get it more now is because I got my PhD mainly to teach. I love teaching, so I think where I get it is now the second hand, where if I see a student struggling and then they finally get it right, I kind of get that second hand, like, yes, you did it, and that's amazing, right? I have students in the Robotarium developing quads right now, right? And the first time that they got them up to not slam into each other, right? The goal was, hey, fly them straight at each other. And that first time, right, it was jumping around. It was awesome. So yeah, I absolutely still get that, especially with the advent of machine learning and all that good stuff, right? I am behind on machine learning, but anytime I see a machine learning algorithm do the thing, anytime I see anything do the thing, it's a amazing thing.
Well, you also know what can go wrong just because you have that real world experience trying to get things work on real robots. You've probably experienced an endless array of things that can go wrong and you're just debugging issues. Tell me about why real world robotics is so hard. What are the key challenges that keep coming up again and again? And what researchers should be wary of but not disheartened by?
Sure. So I think there's two things. The one, if I have to, for multi-agent robotics, the one thing that is really hard is communication, just period. If you're out in the real world, radio signals, lossy comms, it's just period hard. But I think what is really hard in robotics, the thing that is keeping it from really being pushed out into the real world, is it is not one thing, right? If it was, we could solve it and we'd be done. It is a straw that breaks the camel's back problem, where it's maybe this one thing has the wrong type. This integer should have been a longer float, like 32 or 64 float, and then the problems fixed. This message needs to go through at a certain rate. This perception gave us back something we weren't expecting. It's all of these little things that add up. And so it's really, what gives me hope, right? I think we will have jobs for a long time. I don't think AI is going to solve all these problems for us. Is that it's going to come down to very specific solutions for very specific problems for a long time. Hopefully AI will continue and we can get more better cognition, better contextual understanding that we can impart into these systems. But one, it's fun. I think it's fun to run down those problems over and over again, right? You get better at it. You're able to sniff out where these problems lie. And two, because it's challenging, it's more fulfilling when you get it done.
Yeah, yeah. Can you tell me about your double life? So you spend some time in as a professor teaching classes, but you also spend time at GTRI. Tell me more about this joint appointment and also what are the unique perspectives it gives you.
Yeah. Um, so it's fun. I am a very strange individual, especially from Georgia Tech's point of view, because I walk that gap so often. But I tell both sides. It keeps me sharp in ways that you can't by staying on one side. So academia gives you freedom to learn things that you cannot learn in industry just because it's not profit motivated. It's not application motivated, right? I could never stare at ants and justify it to go build robots for GTRI. But conversely, you can also get lost on the academic side, kind of staring at these problems that are academically fascinating and motivated, but are really hard to translate into practicality. So I get to see practical problems. Hey, this is an issue, and sort of bring those hard implementation problems, things that maybe an academic can solve, over to the academic side, and then bring with constraints and things that maybe an academic doesn't know, and then take the academic things that I could see coming in 5 years, 10 years, right? Something that was published 5 years ago, has promise, people have built on it a bunch, and bring that over to the GTRI side and say, okay, we're going to try to get this to work in the real world reliably and robustly. So we're going to take this foundation and we're going to generalize it and robustify it, and then hopefully it'll fly, walk, swim in the real world.
Is it hard? Just wearing so many hats, being a professor, being an industry researcher, you also have a family. Oh, how is it? How have you changed as a person in graduate school to now an instructor, a researcher? How have your priorities shifted, and how have you managed to satisfy all of these different domains?
Yeah, so it is hard. I hope I'm doing it well, right? I talk to my bosses and make sure, but it is hard. But I thrive in chaos. I like being busy. I like having multiple things to do simultaneously. So that's where I think I can do all right in it. How I've changed is I think if you talk to a lot of people as they get older, you don't change much. You just get a more strict schedule. So, right, I have a young son. He wakes up early for school, which means I'm in early, right? No more sleeping till 2 and staying up till 5, right? My sleep schedule is better, maybe, but it's really just having more rigor. And then also, as you get older, depending on how you land, you learn to lead more. So I'm much better at tasking. I was really bad in the beginning. I liked doing things myself, but you get much better at saying at tasking someone and being able to double check what they're doing is correct, and if it's not, helping course correct them. Again, it's a teaching, a mentorship thing that I think you can only learn through experience.
So let's talk about qualities that have served you well as a robotics researcher. You talked about collaboration, delegation. These seem to be really important because robotics is an incredibly collaborative exercise. There's so many moving components to manage. So throughout your time in industry and in academia, who are the people who stand out to you and have made an impact, and what were the qualities that led them to do that?
Man, that's a good question. um so I think, shortlist. Early on, I had Spring Berman, who was my advisor, Ted Pavlik, who was like my postdoc. Ganesh Kumar, who is my older PhD student. So they stood out because they were patient. They were able to help me, and I remember asking like, "How do you guys know so much?" Right? I was very early on, and I was frustrated, and I basically just I broke down a little bit. I was like, "How do you know so much? Right? How do you know all this?" And they also gave me the same answer of just like it's going to take time, right? Just keep at it. This is pass this on now, and I feel the frustration when I say it because I felt frustrated when I heard it, which was this is a marathon. It's not a sprint, right? Think of yourself 10 years from now, right? If you burned out in these 6 months, 10 years from now, you're not going to be as effective as you could be. So that was those were first. So patience is a good one. Patience in being willing to move slower than you would like at times, right? You still need to push when you have to, and then patience in helping others, right? Being there to elevate other people. That's the first. Then when I came to tech, Magnus Egerstedt and Sonia Shinova were big. Magnus really helped me to delegate. He's a master delegation, as well as he's master of storytelling and advertising. So being able to not only do the research but motivate other people, explain to other people, right? I focused on this problem for a year, so of course I think it's important. But now I have to go talk to somebody and convince them that it's important, and I have 5 minutes, right? What's the story behind it? I think that's a big one. And then at GTRI, Gary McMurray, Charles Pippin, Lonnie Parker, these people have really helped me see how do you get things out in the real world, right? And on that side, especially, right, in academics, we're sort of surrounded by people who are focused in academics on the same problem. Out in industry, right, these people aren't, right? So when it again comes back to storytelling, and really proving things theoretically in a way that you can actually explain this to. I always say my mom, right? My mom was a third grade teacher. She is now older. If she watches this, I'm not going to put her age out there, but she's right. What I always say, if I had to explain it to her, right, not a very technical person, how would I do that? And so that's from the GTRI side, right? That kind of idea.
How do you go about looking for mentors? I know it's a broad question, but I think as time has gone on, you've gotten better at discerning what you want and what you don't want. At this stage in your career, what are you looking for in terms of the people you look for guidance?
Yeah, it's a good question. I think in terms of mentorship, I've always been a go with the flow type of person, right? When they come along, they come along. I think almost everyone you can learn from. It's identifying who you keep going back to and think about why you keep going back to them, right? What are the qualities that they are providing to you, or guidance they are providing to you? What is it about them that you keep going back to them? And then try to learn how to do that, because eventually, right, from my point of view, is eventually that person is going to retire or move on, and then there's a hole, right? So how could I fill that hole eventually? And you can't fill every hole, right? But understanding what the things you're going towards, what you're going to them in terms of mentorship for, and then realizing when someone comes to you, hey, I'm old now, the gray hairs are starting to show, and so I need to now provide this back. But in terms of answering your question, I'm really roundabout doing it because I don't know, right? It just sort of, I see it happening naturally and organically.
Absolutely. I do want to take a step back and ask you about swarms again. And one thing I'm curious about is heterogeneity. When we talk about the ant example, there's a key finding from your thesis that you had produced that the group would move at the speed of the slowest ant, which tells me that ants have different capabilities. Not every ant is the same, but it is possible to somewhat design robots in the same way. How does collaboration change when we move from a homogeneous context to entities with different varying capabilities?
Yeah. So it's a good question. That finding was fun because it was one that I just grabbed some ant data from a collaborator and was, why is this happening? It was a cool finding that it published originally. But heterogeneity is a strength and a weakness simultaneously, right? Again, it's a pick your poison kind of thing. If everything is homogeneous, then anyone could do any task. As soon as you add heterogeneity, complexity goes up immensely. But the real finding of that study is no different. Again, this comes back to where me enjoying intuition is no different from humans, right? When I was sitting in the lab, I was thinking, if I had to move a couch with someone, right, they might be stronger, they might be faster. This could be a natural thing, but it could also be, I didn't sleep well last night, right? I'm stronger and faster than you, but I just didn't sleep well, right? And so this natural heterogeneity emerges. So that's kind of where that paper came from. In terms of robotics, you can absolutely put heterogeneity in terms of design. But even if they're homogeneous, you can take, 12 differential drive robots and tell them to drive straight. They're not going to drive straight. So there is heterogeneity built in there inherently. You can also have heterogeneity built in the behavior set, right? Like what they want to specialize in. You have limited compute, you have limited memory. You can't necessarily have everyone do everything. In terms of designing robots and how that's impactful, it can make systems stronger, but they really just become more complicated.
I see. Hmm. Don't you feel that systems tend to be richer because of the different entities within it? I mean, look at humanity. I mean, every one of us is different, but it's because of our differences and our contributions that culture is created, that the entire system thrives. Don't you try envisioning this for robots as well? That maybe one day there'll be robots with different capabilities adding to this whole.
Yeah, so I think that exists already. The difference is, again, going back to kind of swarms, is this idea of emergence versus planned or collaborative, right? The thing you're talking about with humans is, I would say, more of an emergent property, right? It just so happens that our diversity grows this culture, right? And that's homogeneity in a small sector that, when you introduce it to the rest of the world, right, becomes heterogeneity, and things mix and intermingle and become better, right? And that's something that is a cool idea, but we are nowhere near with robots yet, right? We are still very much in the stage of, can I make a robot go from here to here, not hit anything, understand what's going on? But I could see it absolutely becoming an incredibly valuable thing, a valuable add to any robotic system. I mean, in general, in swarms and collaborative, we're already looking, there's already studies out there looking at, surface vehicles with air vehicles, with ground vehicles, or even just a bunch of vehicles with different sensing capabilities. And those sensing capabilities might be heterogeneous by design, but they might be heterogeneous by failure. We all started off with the sensor suite, and two of them have broken on this robot. It knows this. I'm now blind, but I can still hear. What do we do, right? If we have a task, how do we split up our labor? So yes, it is absolutely something that could be beneficial for robotics in the future, but that's, in my mind, so far off that I haven't even really started thinking critically about that possibility currently.
Yeah, it's that practical angle to you as
Yes.
well. I mean, it's hard to philosophize about things that are 50 years down the road. Tell me about what's happening in 5 or 10 years down the road. I feel, given your background, you'd have a very unique perspective on this. How do you see multi-robot systems evolve in industry? Let's talk about warehouses, where let's talk about agriculture. What are some breakthroughs that you see emerging over this time frame?
Yeah, so I think the few that I see immediate, the autonomous vehicles are coming. I haven't checked recently, an agreement between all the automakers that they'll be able to talk to each other. So that's huge, right? That is collaborative, heterogeneous, very, very cool possibility. And so that's something that will be here. Warehousing, I think, will get better. You'll have heterogeneous teams. So right now, right, in your warehouses, typically there are these ground robots, they're carrying around shelves or whatever, and they bring them to humans, and humans have to then do pick and place. I could see these humanoid robots, maybe they don't have to be humanoid, but armed, suction cupped, whatever, able to pick these things up. And so that's something. And then I see search and rescue being something that will be here sooner rather than later. So sending out a bunch of vehicles over a forest out into the ocean to look for something, right? A ship, a person, a group of people, what have you. And then precision agriculture is one that's been on the horizon, but I think is really starting to get here. The research is looking promising in being able to actually do the tasks associated with agriculture. So you can imagine, instead of one tractor going out, you now have 10 or 20 specialized going out to do spot weeding, spot harvesting, right? How we harvest berries and fruit and things like this, right? You go out, you don't rip up the whole field. You find the ones that are ripe and you pull them. Um, Spot watering, right? This patch of dirt is dry. This is in a lower place, so it gets more water. So we use less water and herbicides and pesticides. There are videos out of that laser removal robot, which is my favorite, but you can imagine little ones of those going through the field. So I think those are a few areas where in the next 5 years you could see really being.
You've spoken to people in industry who probably don't have as much of a robotics specialization as you might have. One thing I love about you is you can walk that line. You can explain your thought process, explain it to your mom, like you said. What do you feel are the biggest misconceptions about robotics today that you would like to dispel?
I think there's two, and they're on opposite ends of the spectrum. So depending on who you talk to, people will think that robots are ready to take over the world, right? They are just they believe too much. They trust this autonomous system way too much. And I think the first time I really saw this was just simple autonomy for braking, right? The emergency brakes in cars, right? People would just not hit the brakes anymore, right? The car will stop me. So there's that side of the spectrum. So tempering them and saying, hey, when you see the Boston Dynamic robot doing backflips, here's the video of it falling 800 times, right? Like it's still a hard problem, and so it's not going to be here soon. But then there's the other side that completely do not trust at all, right? Like these systems, they won't work. They have very specific niches, and so bringing them back towards the center, showing cases of robots working out in the wild, being able to trust them is something that I see. So it's pulling both of those ends of the spectrum back towards the practical middle is the thing I see most in industry.
Trust is the heavy term, and you'd mentioned search and rescue earlier as well. I am personally quite interested in the area of legibility. We've already talked in human robot interaction, there's legibility of robot motion, but I'm wondering if legibility of swarm behavior is something that should be considered as well. So if I'm a firefighter going into a building, I want to know what the drones above me are trying to do. Do you have any intuition as to how this potential problem could be solved?
Myself, no. So I have a student who's now over with Julie Adams, who is one of the leading researchers in this kind of human robot human swarm interaction space. I think it's a fundamentally hard problem because if you're looking at a screen or you're looking at robots around you, you can only track so many. So if we're talking truly swarms in hundreds and thousands, that's not, you can't track all of those simultaneously. So I think it really does come down to abstracting away, right? The quads are going out and they are looking for survivors, right? They're looking for hotspots. They are just, knowing at a high level what each robot is doing, maybe not individually. And then it's trust, right? If we bring this back to people, which people are a bad example of swarms, but when you are driving, you don't watch everyone, right? You assume that you look at your local neighbors and assume everyone else is doing things correctly. In business and anywhere that humans are working organized as a group, you kind of abstract things away and you just trust that people are doing the right thing and then identify when people are doing the wrong thing. But I think that's probably the best we can do currently. But again, I'm not an expert in this. I think it's a fundamentally hard problem that luckily I don't have to work on right now.
Yeah, yeah. You're busy with the Robotarium. What do you, I guess, moving back to the Robotarium and the kinds of things that it's enabled for the community? How do you create a system that's convenient for all the stakeholders to use?
Yeah, so there's two parts to this. For the first is what input to the system is everyone going to use. So for the Robotarium, right, they're ground robots. You send velocity commands to them, right? You move them. And then the sensor, there's a bunch back there. When we started, we gave them, like a researcher does, here's the nonlinear system, control the nonlinear system, right? And the feedback almost immediately was, hey, I don't want to do that necessarily, right? I might want to do position control. I might want to just say robot go that way, right? So we added in these abilities to use these higher level control schemes. In terms of automation, again, it's a very specific niche. So for the Robotarium, right, the first step is building a reliable hardware software infrastructure, which I'm just saying, but that's an extremely daunting task, right? And being able to identify, your 101 engineering, what's the place that this is going to break, right? What's the weakest link, and designing such that you can either address that or replace that. So for our ground robots, right, they run hundreds of hours, and we use these very inexpensive motors, and those inexpensive motors are the point of failure for these. And so we've designed them such that you can just pop them off and pop them back on. So that kind of thing helps make the automation. And then knowing those fault points, right? If something goes wrong, we don't necessarily need to know everything that's going to go wrong. I just need to know the output signal that is going to say something is wrong. So after every experiment or just maintenance wise, the system autonomously charges itself. The robots know that they're charging, all of that good stuff. And so the centralized system, if something is not charging, it knows something is wrong. So we don't know what exactly it is. Could be that the tracking system is off, could be the network is off, could be something has happened. And so when that occurs, we come to the humans. At the end of the day, eventually it's I can't resolve this, right? Robot stuck on the bed, something has gone wrong, I can't flip the switch. And so send out an email, send out a Slack message, send out whatever to get the humans on the case. But so it's building robust software and hardware infrastructure, knowing where your fault points are and making them as sturdy as they can be.
Awesome. Yeah, because I do see that this ties in directly with legibility and abstraction that we were talking about earlier. Because as the Robotarium gets bigger, it might get even harder to pinpoint the exact reason that the fault may have happened. So, creating that intuitive interface between the humans and the swarms would be really, really important. And I feel your work with the Robotarium could enable such an application. Moving forward, what are some creative or unexpected uses of the Robotarium that you've seen over your time managing the facility?
Yeah. So to start, we don't know almost anything that's being put on here. So when you submit something, right, it's your code. Unless you ask, we do not look at it. It's automatically run, all of that good stuff. Magnus was still with us. The New York Times wrote us up. The Wall Street Journal wrote us up. And the headline I still like to parrot. It's these robots. This robotics lab has no idea what its robots are doing, right? And so that's, I would say, for 90 to 99%, I have no idea. If you can guess what 20 robots are doing going around, awesome. The ones that I do, so one was an ant colony queen selection algorithm, and the only reason that we knew that, right, it was submitted from ASU. I saw the email and I'm like, oh, I know this person, and so I messaged them and said, hey, what are you doing? And it was a cool queen selection algorithm for an ant colony called Harpagnathos. When their queen dies, the typically in an ant colony, queen dies, colony can't go on because queen's the only one that makes new ants. These ants are special and everyone can become the next queen. And so they go out and they have a fight. And so these robots went out, they were having a fight, simulated fight, black fight pit, colored robots for fitness. And the cool thing is you don't wind up with a single queen, you wind up with an oligarchy structure. And so the research question they were going after is, what are the rules, right? How often do you fight? Who do you fight? When do you decide to stop? Right, and that oligarchy is always 10%. So they were doing that kind of testing. So that's one really cool one. Ones that I've seen that I can really only guess at. There's been some kind of fabric transport. I believe they published recently. I'd have to find it, but they're for robots. There's a graphical mesh between them that moves, and that's really cool. There have been some social network ones that are lost to time now, older. But there was your Facebook logo, your Twitter logo, that old Instagram logo, and the robots were moving around, and the bubbles were growing, and network topology was changing. So stuff like that is cool. But again, I think last one I'll say is because some people from Columbia came to Georgia Tech. They were doing some EEG. So this is a rare occurrence where you can come to the Robotarium, but they were doing some EEG filtering and playing music, and they were trying to make the robots dance happy or sad, and they were changing color schemes, and so that was really cool. In general, I'm sure there's a ton more, but one of the main lessons that I've learned, at least from opening the Robotarium, is if you build it, if you make things open source, people will do things with your platform that you would never have imagined to do yourself, right? I would still be doing formation control and coverage control, these very fundamental robotics multi-agent system things, but there are people all over the world doing painting and art and wild stuff with robots simply because they don't have to maintain them, they don't have to build them, they don't have to have the expertise, but they can still leverage them. That's a super cool quality.
It's awesome that diverse experiences come together to create this magic. As I'm sure you're aware, you've had a diverse set of experiences that have led you to become the person that you are today. I want to ask you, in terms of the future, where's the Robotarium headed? What are some cool things that we can expect to see?
Yeah, so the future of the Robotarium immediately, next 2 years, twofold. One is I want to have quads. So I would love, if I had infinite money, space resources, I would love to give people access to ground robots, walking robots, underground robots, underwater robots, flying. So the immediate next step is flying robots. Those are really hard for three reasons really. One, we have kind of solved is the I don't know what joystick to give people, right? An extreme, someone who's an expert in it can build trajectories. They can maybe even do the torque control straight on the motors. Someone who is a novice still wants to fly robots, and maybe we give them waypoint control, but having that balance is really hard. Two is when a ground robot something goes wrong, it just sits there, and that's totally fine. When an air robot something goes wrong, it's a rock, right? If it was accelerating upwards, it's still going to accelerate upwards, hit tracking camera that's very expensive, all of that good stuff. So that's the really hard challenge, and robustifying it is really hard. So that's the first. The second is I really have seen a growth in educational use. We originally built it for researchers by researchers. And about our use is probably 60-40 research to education, maybe 50-50 at this point. And there's been a lot of push to make it accessible to K through 12. Like I said, I think robotics is a gateway drug to math and science. And so the other push is to start getting it into the classroom. So building curriculum around it, making block programming interfaces, doing stuff where you can start doing logical thinking. You can start understanding programming and robotics and really start beyond doing theory in this kind of stuff or watching a simulated entity, also building intuition into, like we talked about, straw that broke the camel's back. These little things can add up, and the culmination of errors can make everything fall apart. So those are the two immediate. And then after that, I would love to, probably not for general public, but build remotely accessible research platforms. So maybe an Atlas robot, these big honking arms, stuff that maybe is more consequential, more expensive for the research community, and potentially go outdoors. In Atlanta, it's hard to find a lot of outdoor real estate, but I would love to have an outdoor Robotarium as well, right? Start dealing with the real world, but that's a farther out there idea.
Do you ever worry, by the way, that you're sleeping and the drone just crashes against the wall? Just asking.
Yeah. So yes, while we can run 24/7, we've proved it out. I think we ran it for like 3 weeks and it was fine. So truly we run it from when the first person shows up, so like 6 a.m. ish, until the last person go home, so like 11, 9 p.m. ish. We do that because I found, at least, right, we get emails when things go wrong. It would always be at like 3 in the morning, 4 in the morning. And so the choice at that point is either, okay, drive in, go fix it, or just let the test bed die, right? It's not going to do anything, but the robots are slowly going to drain their battery, and then I have to deal with it the next day. So yes, absolutely have that issue. We do leverage barrier certificates, and so they won't crash into each other. But again, that's a theory thing, right? Theoretically, with the underlying assumption, if everything is working, if tracking's fine, communication is fine, right, then they will never crash into each other. But as soon as something goes wrong, then everything breaks. And so yes, absolutely have that scare. And that's the reason why, while it does roll autonomously when it's there, usually we try to run it when someone's at least in the area and it's a 5-minute walk to go figure out what the issue was.
Is there something special about Georgia Tech specifically that made the Robotarium possible? And even now, is there something special about the institution that leads you to run the Robotarium, have the joint appointment? What are the factors that have kept you at this university for so long?
Yeah. So yes, I think the biggest thing is the diversity of the faculty and students. In terms of their expertise and who they are, it's a great place to work. And in terms of ideas, I can go and find an expert in any subfield, right? If I want to do rehabilitation robots, I've never touched that. I know there's a list of experts to go do rehabilitation robots. I want to do quadrupeds, two-legged walking robots. There are experts sitting over there. I want to do networking. I want to do perception, right? I can go find those people. And so that diversity really helps from a research and educational perspective, right? That's enabled um, a lot of the research that has brought the Robotarium to bear. The other part of it is, institutional wise, the Office of Institute OIT, they were crucial in getting the Robotarium stood up, right? There was a lot of support in letting this happen. As you could imagine, if when Magnus and I are proposing, hey, we want to let anyone put executable scripts inside. I want them to be able to submit. It's going to run on a computer in the Georgia Tech network, and I want you to just let us do this, right? So they were very supportive in getting us the wireless networking, helping us with cybersecurity stuff. So again, the collaborative nature, the willingness to put out to make these kind of grand ideas happening and just letting us go after the grand idea is something that I think is unique and why we've been successful.
Awesome. And for researchers coming in to Georgia Tech, and even those that are already here, just cumulatively taking in all of your life experiences so far, what advice would you give them for traversing this dynamic environment that we're in currently?
Yeah, I think keep talking to people. Do what you enjoy. I think, do what you have to because you have to, but do what you enjoy. I think having something that you enjoy doing every day is a crucial part, and leverage the interpersonal connections, right? Don't be afraid to go talk to people. Don't be afraid to, if you're at Georgia Tech, everyone is brilliant, right? So leverage their brilliance. I'm, again, a collaborative swarm guy. The group is always smarter than the individual. And so while you might be an expert in something, go out and talk to others, right? Recently, I've been talking to education experts because I don't know K through 12, right? I have no idea what the standards are. When I was in high school, we didn't have Arduinos. I was in the first programming course where we were writing things on paper still. So I have no idea about that. Go talk to the psychologists, the HCI people, the psychologists, interesting, ideas in we know how to make robots move. What we do to make them move, but how should they move? If you're going to take care of grandma, how should it walk in? Not necessarily is it stable, but not like this. Don't scare her, right? But that's a psychology question. And HCI, like you're talking about, if I want to make an interface for someone to control a robot, what does that GUI look like? I'm not an expert in that, so going and talking to other people, and beyond even technical, talk to them about your day, right? Your family, go to lunch with them. Having that balance is an important thing beyond just being a technical expert in something.
Yeah. Well, Sean, thank you so much for your time. And you already know this, but I'm very grateful that you're part of our community and you run the class and you've inspired so many people. I'm just really grateful that you're in the community, and I hope you keep doing the amazing things that you're doing.
Yeah, thanks for doing this. Thanks for having me, and you're most welcome.